Right, welcome everyone. For today's ZX meeting, we've got Kostia Chardonnet telling us about geometry of interaction for ZX diagrams. Take it away.
So thank you very much. So I'm a PhD student at University Paris with Benoît Valéron and Alexis Sor, but this is a joint work I did with Benoît Valéron and Renaud Villemar. So I met Renaud Villemar at our lab. He was a postdoc, and then we talked a bit about what we were doing. So I was working on ZX calculus, and I was more coming from linear logic and proof theory. And when we talked, we realized that ZX calculus and something from a linear logic called proofnet was a bit similar. So try to look into the connection between the two of them. There is already some existing work about that, like Rasdon-Kahn proofnet, for instance. So we try to apply tools from linear logic to ZX diagram, see where that could get us, and that's the work I'm going to present. That's what we got at the end. So I'll do just a very, very brief reintroduction to ZX. So the generator we work with as R00. So we have identity, swap, cup, cap, only the green spider and the Adamar. We don't care about the red spider since you can just recover it by composing a green spider and Adamars on all the input and output. So you have the usual composition and the standard interpretations that send ZX diagram to a matrix of a complex number. So the semantic of all the generator. So for the green spider, you just have a big matrix with a one, the top left, most top left indices, and exponential I alpha in the bottom right. So basically what it does is that if you get only input of 0, you only produce input of 0, output of 0. If all your input are in 1, you get exponential I alpha of all the input at 1, and otherwise you get a 0. So, and then you have the Adamar gate, which is the usual change of basis, which gets you the which send you from the 0, 1 to the plus minus basis, and you have all the usual wires. So the identities are those nothing, the swap, that just swap argument, and the cap and the cups that produce an internal pair and that does the dual operation. So as usual, the semantic work by decomposing your diagram as in the usual manner with a tensor product or the usual sequential composition. And then you can just look at your diagram, find the decomposition, and compute the semantic of all the smaller parts as given by the semantic of before. And then you get some matrix. So this is the CNOT diagram, which gives you the CNOT matrix with some scalar of 1 over square root of 2 that is just in front of it. It's not really important. So that's just the ZX we work with. So only green spider and nothing crazy happening. And what we want to do is relate it with what we call a geometry of interaction of it. So geometry of interaction is a tool that allows us in linear logic and in proof theory to analyze the computational content of some proof seen as a graph. And so that's what we'll try to do here, is that we'll try to look at our ZX diagram just as some kind of graph, have some what we call tokens. So you can see token like in an intuitive manner as just information that flow through the ZX diagram. So in the same way that in a quantum circuit, you can say, okay, so you have like your qubits that flow from the left to the right. You can say that there are some kind of tokens. So it's a bit similar in spirit. And the token will travel through the graph. They will capture some computational content. So in linear logic, it's just what does the proof compute? And the idea is just to bring some kind of operational semantics to the ZX diagram. And some particularities that in linear logic, well, you just have one token that travels the graph. While since we are in a quantum world, we need tokens that are a bit more evolved. So in particular, we need superposition of tokens. And we can also have multiple tokens that are at different places through the graph. And therefore, the token can collide with one another. And this is a particularity that does not happen directly, we'll say, in a linear logic. And so in some way, we'll see that through this token machine, we can, in some way, reintroduce linear algebra in the ZX diagram but in a more controlled way. So geometry of iteration for computation has already been studied mainly in the work by Dallaglio, Fabien, Valéron, and Yoshimizu, in which they use token machine in the context of some kind of modified proof net of linear logic mixed with some kind of quantum circuit. The idea is that so their token will just travel through the proof net, and they will be synchronized by some gate at some point that will ask that all the tokens are present in order to keep evaluating the proof net. And so they can also have, because of that, they have some kind of control flow of their program that are purely classical, while we are more interested in some kind of quantum control flow of the program. And also their tokens are mainly classical, so there are no notion of superposition. But compared to the ZX diagram and the work we did, they have a notion of type. So for instance, they can have like a product or coproduct, which we don't have in the ZX calculus. So we just need to do one little trick to the ZX diagram, is that we need to give a name to each wire in the ZX in a diagram. So by convention, we'll write A1, A2, A3 for the input wire, and B1, B2, B3 for the output wire. So we'll read the diagram from top to bottom. And the wire in the middle will just be E1, E2, E3, etc. So as given in this example. So you can see between E1 and E2, there is a cap. So each side of the cap has a different name. And so you have you can ask for all the input wire will be A0, A1, the output will be B0, B1, and B2, and all the edges will be so the set of the input and output and everything in the middle. And the idea is that a token is a three type containing three information. The first one is the location of where your token is in the diagram, so just the name of the edge. Then you have a direction, either the token is going up in your diagram or is it going down. And then the token will carry some state, which is either 0 or 1. And then you have the notion of a token state, which is basically a sum of product of token with complex coefficient. So for instance, if you take the small diagram on the right, a token state will be, for instance, having a token in the wire E1 that is going down in 0, in a product with another token in the wire E3 prime going up in the state 1, and the two of them in a sum with a token going down in E1 in the state 1. And so that is that each token will move and the way they move is described by purely local rule, and they will modify the global token state as they move. And this global token state will capture the computational behavior of this ZX diagram. So in order to make things simpler for this presentation, we instead of writing the token state as a sum of product of a three type, we'll just represent everything graphically, but it is completely similar. So the token will be drawn by some black dot on the diagram with an arrow describing in which direction they are going and the state next to them. So the product represents the fact that you have multiple tokens on a single diagram, and you can have some weight sum of this diagram which represents superposition. So for instance, here you can have alpha of some diagram with a token in 0 plus beta of the same diagram with the token system in 1. So the first rule that we'll look into are the rule for collision. So is what happens when two tokens are going in opposite direction in the same wire. In that case, we have two different possibilities. Either we consider that the two tokens are in the same state X, in which case we call this a positive collision, and so just the token disappear. So in the product, that just means that the two tokens will rewrite to 1, and so it's a neutral element of the product, so nothing happens, and they just disappear. The other case is that if the tokens are in the opposite state, so they will rewrite to 0. So basically, they will produce the empty diagram, and so this corresponds to the absorbing element of your product of token, and so the whole product will disappear. Then you have the diffusion rule of your ZX diagram. So the first one is the green spider, in which, so if you have some green spider with a phase alpha, with a angle alpha, and you have a token going down in the state X, it will rewrite to exponential IX alpha of the same diagram, but this time on all the other input and output wire of your green spider, you have a token either going up in the input or going down in the input in the state X. So basically, the token has duplicated itself in every input and output wire. So this can be seen as, so if you think about the semantic of the green spider, it will ask that all the inputs are in the same state, so in the state 0, for instance. And if it is the case, all the inputs it returns all the input at 0, basically. And this is what is kind of simulated in some way. So here you get only one input in your token. So say it is 0, you need to ask that all the other inputs are also 0 for it to evaluate properly. So what we do in some way is that we assume that all the inputs are 0. So by having token going down in the output, it says that, okay, I assume that all my inputs were 0, so I can produce all the output at 0. But I will send back token in the input, so the token going up in the state 0. And so they will search for other token to make sure that if other tokens were about to come, they are also in the state 0. Because if they are, they will do a positive collision, and so it's okay. But if one of the inputs, there was another token that was about to enter the same node, but the same in the state 1, we will have a negative collision, and so the diagram will disappear. Finally, you have the Hadamard gate, in which if you have some input token going down in the state X, you get 1 over square root of 2 of superposition of your diagram. In one case, in which the token in the state 0, in the other case, the token in the state 1, and you have it plus, and you have, so it's either in a plus or in a minus between those two diagrams. And finally, for all the wire, absolutely nothing happens, just the token flows through it and move along. So we'll give a concrete example on how it works. And for that, we go back to the CMAT diagram of earlier. So just remember, it's semantics. So if you put as input the state 1, 0, you get as output 1 over square root of 2 of the state 1, 1. So having as input the state 1, 0 will be represented by giving 2 input tokens, the first one in the state 1, and the second one in the state 0. And so we'll see how this token state rewrite, and we'll see which result we'll get at the end. So first, let's decide to rewrite the token on the left. So it goes through a green node. So what it does is it just duplicates itself on the 2 outputs. And then I will always rewrite the token in purple. So we will rewrite the token on the right. So it will go through an Hadamard. So we'll get a superposition of 2 diagrams. And because the token in the state 0, we get a plus in between those 2 diagrams. And so you can notice that on the left diagram, we get the state 0, while on the right diagram, the state that is now in the token is now on the state 1. Then we can go again through the green node, just because it's simple, so the token will duplicate itself. We do the same on the right diagram, because we can. And then we'll decide to rewrite the tokens that will go through the Hadamard gate. So this time it is in the state 1, so we'll get a minus between the 2 diagrams that are produced. And so we can decide to, and yeah, we get another 1 over square root of 2 that appear. And we can decide to do the same again on the diagram on the far right. And and just one thing that I forgot to mention is that all the coefficients 1 over square root of 2, you can simplify them, you can distribute them, etc., etc. So we'll rewrite the diagram and we'll just simplify a bit the coefficients. So we get 1 over 2 of this sum of diagram. And you notice that there is 4 different collisions. So the diagram on the left the collision is positive because the two tokens are in the same state, so nothing happens. The token just disappear. When in the other case, the tokens are in opposite state, so the whole diagram will disappear. This happens again in this diagram. And finally, for the last diagram, the two tokens are in the state 1, so they just they just disappear. Finally, we'll just rewrite in one step the two tokens at the bottom that go through an Adamar to end up with this state. And here, what we can notice is that the first diagram is the same as the third one, and the second diagram is the same as the last one with the token. And the first diagram, and what you can do, technically, is the first diagram minus the third diagram, so you can make the two of them disappear. And the first diagram and the second diagram plus the fourth diagram, so you can just sum them. And you end up with this 1/square root of 2 of your diagram with two output tokens both in the state 1. And so if we decide not to represent this graphically, but through the rewriting, and you say that your two input tokens are A1 and A2, and the two output tokens are B1 and B2, you will get this at the end as a rewriting step. And the intuition is that the output token of your diagram will represent the ket that you obtain, that we have obtained at the bottom, so the ket 1, 1. And so the intuition is that an output token that is going down will represent a ket, while a token on the input that is going up will represent a bar. Okay, so I cannot cheat in this example in the fact that I choose a specific rewriting strategy, which is that as soon as there is a collision, I delete. And in fact, if we decide to take an arbitrary rewriting order, so for instance, in this example in which you rewrite the purple token as again, you can end up in an infinite loop. And this is something we want to avoid, to have a non-terminating computation. So the strategy is to always do a collision when it is possible, and never ignore a collision. So the transition system is defined as being exactly one diffusion rule, followed by all the possible collision rules until none of them apply. And this is a strategy that I did in this example. If you don't do that, you can end up with non-terminating run, and it's not something you want. But this is not enough to say that you have a system that is that computes something interesting. In fact, there is multiple things you want to avoid. The first one being multiple tokens on the same edge that does not collide. So for instance, if you have some edge E, you can have like two tokens on the edge E going down in the state X, and so they will not collide. And this is something we want to avoid, because if we have that, we cannot relate the final state of the token machine to the standard interpretation of the ZX. And also, just doing the collision may not ensure non-termination, so we need to be careful about that kind of thing. So for that, we just have two invariants, the first one being called Well-Formedness, which will allow us to avoid any bad configuration. And the second one is called cycle balanceness, which will give us termination and the confluence of the rewriting system. So for that, we just need to define the polarity in a path. So take any oriented path in your ZX diagram, and you will look at all the tokens that are in your path. Basically, if the token is going in the same direction as the path, then its polarity will be +1. If the token goes in the opposite direction of the path, then its polarity is -1, sorry. And if the token is not on the path, then the polarity is just 0. So in this example, you have two tokens. First one in the edge E0 on the left that is going down, so it follows the blue path. And the other token more on the right on the edge E3 is going up, so it's going against the path. So you get +1. So if in order to take the polarity of the whole path, you do the sum of the polarity of each token. So you get +1 - 1, and so the polarity of this token state is just 0. And so we say that ZX diagram is well formed if for every path, while looking at the token on it, the polarity is between -1 and 1. So the intuition is that if you may have multiple tokens at some point on your path, but they will all cancel each other out until there is at most one token at the end, either following the path or going against it. Or you can have no token at the end. We have that the well-formedness is preserved under the reduction rule. And finally, another theorem that says that if you start in the initial well-formed set, you cannot reach a bad configuration. So bad configuration being, for instance, having two tokens on an output going down and that do not collect. And finally, we say that the ZX diagram is cycle balance if for every cycle in your diagram, the polarity of the token on it is just 0. So once again, the intuition being that if you have a cycle and multiple tokens on it, at some point they need to each cancel each other out so that you end up with no token on the cycle. So that at the end, like you terminate. So you have a notion of termination. So if you have a ZX diagram and some token state that is well-formed and cycle balance, then the token state, after reweighting, it will terminate at some point. And all of this leads us to the main theorem of the paper, which is that you can recover the standard interpretation of a diagram through this method. So if you take any diagram D and you take some edge inside the diagram, some edge E, you can set an initial token state, the token state T, as being E1. So you take the edge E and you have a superposition of token. In the first case, you send one token up and down in the state 0 in superposition with one token going up and down in the state 1. So what we get is that this initial token state is well-formed and cycle balance. And also if the semantic of the diagram D, so this huge formula of if you have some coefficient lambda q, sum with this coefficient lambda q, and you have some ket in the state y1 to a ym and somehow with the state x1 to xn, then the state T, after reweighting, will give a token state, which is a sum of products. In the first case, you have all the token on the output wire and all the B1 in the sex Y1. So as the ket of this that you get from the standard interpretation, so the green underline. And for every token that will end up in the input and going up will represent the bar of the standard interpretation. So you really recover the standard interpretation. So you just need to be careful is that when you do that, you just have not to do an initial collision. So the way to think of it is that on the wire E, the token going up and down in 0 are going up and down, but like they won't collide. So in some way, you can consider that E you can take any wire and you can split it in two by putting a green spider in the middle. So this is correct by the rule of the ZX calculus. And you send, and on the wire at the top of the green node, you send the token up, and on the bottom, you send the token going down. And so with that, what it means is that you can just recover the standard interpretation of the ZX diagram. So in the same way, if you don't want to recover all this interpretation of the ZX diagram, and you just want to evaluate it to some state, we can did as I did in the example with the CNOT gate, and just input some token on the input wire of your diagram in the state that you are interested in. So this concludes what we did for the for this token machine for the diagram. So the idea is that we just wanted to have like some kind of general framework to see the ZX calculus, and in a more let's say like a local way. So we have like just local reweighting rule at each step. And it's a more operational approach to ZX calculus than just computing the usual standard interpretation. And it can also be quite easily adapted to other extensions of ZX calculus. So we did it in particular to mixed process and also to some overpass semantic. In fact, when you add new generator to the ZX calculus, you can just add one reweighting rule to your token machine. And if you choose the correct rule with the invariance that we put at the beginning, you should, without too much problem, get what you want. In fact, it's a bit more powerful. This token machine can be adapted to any kind of tensor network. in which you just need, so if you have a tensor network and you have some wire of some dimension, you just need, instead of having the state of your token just being 0 and 1, you need to have one possible state for each, one state for each possible, well, let's say, if your dimension is like n, you need n different kind of states, so 0, 1, 2, 3, up to n. And with that, you should be able to do something similar for any kind of tensor network. And so the main idea of that is to initialize to, well, that one of the main motivation for that is that it is the first step toward being able to add types in this ZX calculus, and in particular having a stronger relation with linear logic and proofnet. And so this is what gives future work that we've submitted to QPL and MFCS this year. So maybe we'll have the opportunity to present it at QPL this year. And also, yeah, no, I forgot to put this line. And also another thing we want to do with that is being able to add notion of recursion and trace in the ZX calculus, and maybe also notion of inductive type, for instance, inside the ZX calculus. So this is also something we are thinking about and working on actually. So thank you for your attention.
Thank you.
If you have any question?
Yeah, I can see some hands up for questions. I'm not quite sure who went first. Let's have Renaud first, maybe.
Oh, actually, that was a clap.
That was a clap, sorry. Okay, I misinterpreted it. Apologies.
No worries.
Are there any questions? So I've got a couple of questions. So in the example you had of going into an infinite loop in the evaluation, I didn't quite catch what went wrong. I assume, like, sort of from what you explained afterwards, there was some way in which people weren't obeying the rules. But
so if you take, so from the diagram in the middle, with the arbitrary waiting order, if you look at the path at the cycle, then you will get that the polarity will be won't be 0, basically. And so what happened is that, well, no, it will be 0. Okay, so just what happened in this case is that, so you rewrite the first token on the left, so it duplicates itself, the purple token. And then if you decide to ignore the collision here and to just rewrite the token in purple, then you see that it gets back to its initial position on the left. And so you could do this forever and just have an infinite amount of token in the state 0 going up and down on the input and output.
Okay, right. So yes, so you just kind of move it past the other one without actually.
Yeah, you just move it past it and you go through the green node and
the spider again. Okay.
And this happens when you ignore the collision. So just below, when you do the collision, then the 2 tokens disappear, and you just get an output token in the state 0.
Yeah.
And this is kind of current with the semantic of the diagram, because it should just be an identity. So if you input 0, you should just get 0 as output.
Yeah.
But if you don't do the collisions, then you get weird stuff in the input and many output at 0, and it's weird and does not have any good meaning nor intuition.
Right. Yes. Yeah. I guess I wasn't quite hadn't quite noticed that sort of collisions weren't mandatory at the beginning, like that you could just ignore them and continue rewriting otherwise. But yeah, thanks. That's cleared it up. And then on slide 19, I had a question. There was sort of at the top, you defined this T, where you've just kind of introduced this one token. But then at the bottom, you've got T0 plus T1.
Oh, yeah, this is about the copy paste.
Right.
So T0 is, so you take T, you have this sum. So T0 is on the left and T right.
Right.
Or
yeah.
rather.
Okay.
So basically, it just says that you rewrite each part without doing the initial collision. Because here, technically, you could say that there is a collision there is 2 collisions in T, but you should say ignore those 2 collisions, So at the end, you get T0 plus T1, and this is what you get.
Yeah.
So just, yeah, it's poorly written. But yeah, just ignore the initial collision, rewrite each part of the sum to get T0 plus T1, and this is what you get.
Okay. Yeah, thanks. Does anyone else have any questions now?
Yeah. So these tokens, I can kind of view them as like a red pie face being pushed through the diagram, right?
As a what, sorry?
There's a X pie face.
X pi, yeah. If I understand correctly, then
Like a red spider with one input, one output, and phase pi, or I guess phase, yeah, depending on.
Oh, yes. Yeah. So when we did the this example, so here on the left diagram, the two input tokens, 1 and 0, it's just adding a ket 1 and a ket 0 as diagrams that you just compose to your CNOT. If this is what you meant.
Yeah, and then when you push it through a Hadamard, you just write this thing as a sum. Like you actually get a green spider, but you just write this as a sum of red spiders somehow, or maybe it should be viewed as like a ket 0, ket 1 that you push through a diagram, so it cuts the wire or something. I'm just trying to relate it to stuff I'm more familiar with, seeing if it's.
So I'm not sure what you mean by cut the wire.
Like if we have a token X on a wire, if I view this as sort of a ket 0 or ket 1 depending on X, being input into the wire, and then I push it through the spider, which removes that wire, and I get a smaller diagram.
Yes.
I think this would also give you, I think, like a terminating rewrite strategy for like calculating stuff. But
I guess that will work. Well, I guess that will work. The thing that we just wanted to change the spirit of a reason why we didn't try to directly like rewrite diagram is that in the spirit of geometry of interaction and linear logic, you just see your diagram just as a graph and you never modify it. So we never apply any of the rule of rewriting of the equational theory of the ZX or anything like that. And we just don't change the diagrams. We just like a rewriting system, but the diagram is just a static object that does not move.
Right. And your terminating rewrite strategy always calculates the interpretation of the linear map.
If you take this as an initial state, this state T as initial state, then yes, it will always compute the semantic of the diagram, the whole semantic of it.
And what would happen if you only do, say, T0, so not the T1 part? Is that not cycle balanced?
It will still be cycle balance, but you won't compute the whole semantic. I don't know if that's good intuition to what you will compute, but you just like miss half of the semantic of the diagram. So in some way, like how can I say? Okay, if I go back to this, so basically what you could say is that let's say that the diagram, the wire you take to compute the whole semantics is the one on the left, so the one where you have a 1. So if instead of having 0 going up and down plus 1 going up and down, you just get 0, you will just compute like a partial map in some way. It will just be what happened when to your diagram when one of its input is 0 and the other is whatever. So you will miss half of the semantic of the diagram.
Okay, that makes sense. Yeah, thanks.
So when you're doing this, is it, yeah, like here you've got these tokens with two different states. I'm kind of wondering, like, so you say this can be extended to other graphical languages as well. So you could potentially do a similar thing for ZW. Have you looked at that at all?
So what is ZW?
It's the one that has the W spider, which is like ket 001 plus ket 010 plus ket 100.
So we didn't do it for this one, but well, what we've can and not proven is that this could be technically adapted to any kind of tensor network. So I guess ZW is also one. So I guess it should work for it if you just take a good rewriting rule for this node.
Mm-hmm. Yeah, so I'm just wondering, because like the sort of these tokens moving through the diagram, like so ZW, or at least some fragment of ZW, has this alternative interpretation from physics where you can look at it as a network with particles moving through it, which is quite similar to this token case. You'd have the difference that like the particles wouldn't have a state. It would just be like the presence or absence of a particle that denotes the state. So, but it does still seem quite similar. So I'm kind of wondering
I'm
about.
really not familiar with the ZW, but I could try to look into it and tell you a bit if I found something like how similar it is.
Yeah,
but
no,
just like that, I'm really not familiar. I really don't know this language, so.
On Discord, maybe. Yeah. Any other questions? I guess I have another sort of, probably quite naive question, because again, I don't know very much about the background of this stuff in kind of proof nets and linear logic. So I mean, there's obviously like other ways we also have of translating a ZX diagram into its interpretation. And so I'm wondering kind of, what, like, is there sort of some useful way to see like why this kind of token formalism is specifically useful? Like, because is it mainly because it draws this connection to other like
so for me, okay, so for me the main reason, so I guess the false ZX diagram in and on itself, it might not be the most like useful tool in the box, you can say. But it's more like, at least in logic, the use of those kind of token machine is that it is very useful to just study at each point in a very local manner what happened to the control flow of your program in logic. And so in particular, so in ZX, you don't really have a notion of you don't have an intuitive and like easy notion of control flow. And so the idea was that starting with this token machine, what can we add to ZX to have like a good notion of control flow and potentially quantum control? So this is what we did in the paper we sent to QPL. And the idea was more like, as first step, how can we just define it on the ZX calculus? How can a token machine work on a quantum graphical languages? Because token machines usually are just made in a classical way, and the same it is in a purely quantum way. And then what can we add to the language to have like just type in the ZX calculus? So for instance, having so you can always add a tensor, so this is very easy, but you can also consider coproduct, potentially some inductive type, so this is work in progress and stuff like that. And the semantic of a token just going through a plus or a tensor or something like that is very intuitive, because you can just see it as a term of a programming languages. So it's very easy to understand what the semantic of it is. And so it's more like a tool to help us develop new semantic for extension of the ZX calculus, in particular one with types and product and coproduct, etc., etc.
Okay,
so this was the main.
Yeah, no, that connection to control flow. Yeah, that's useful. Is your like the paper you mentioned you've submitted to QPL, is that on the archive or?
Yeah, it's one I sent on Discord like last week or
Right.
2 weeks ago.
Okay, yeah.
I just realized that actually we didn't put the token machine in the paper because there was not enough room for it in the submission. But we have a token machine for this, like ZX with type language that we have in the paper. And yeah, I should put it on update it and put it on archive.